property, finite intersection property and local compactness. So first of all, what is finite intersection property? A collection C of subsets of X is said to have the finite intersection property if for every finite subcollection C1, C2, Cn of C, the intersection C1 intersection C2 intersection Cn is non-empty. If this intersection is non-empty, then we say that the collection C of subsets of X have the finite intersection property. Now we will prove some theorems related to finite intersection property. Let X be a topological space. Then X is compact if and only if for every collection C of closed sets in X having the finite intersection property, the intersection of elements of C, where C belongs to C, of all elements of C is non-empty. Suppose we are given a collection A of subsets of X, and let C be the collection of complement of A, means X minus A, such that A belongs to A be the collection of their complements. Then the following statements hold. A is a collection of open sets if and only if C is a collection of closed set, because C is a collection of their complements. The collection A covers X if and only if the intersection C, such that C belongs to C, of all empty elements of C is empty. The finite subcollection A1, A2, An of A covers X if and only if the intersection of the corresponding elements Ci equal to X minus A of C is empty. So the first statement is trivial, while the second and third follows from De Morgan's law. The De Morgan's law means X minus union of A alpha, where alpha belongs to J, is equal to intersection of X minus A alpha, alpha belonging to J. For two elements, De Morgan's law states that A union B complement is equal to A complement intersection B complement. So similarly, X minus union A alpha, alpha belonging to J is equal to intersection of alpha belonging to J, X minus A alpha. The statement that X is compact is equivalent to saying that given any collection A of open subsets of X, if A covers X, then some finite subcollection of A covers X. This is by the definition of compactness. So we can also state this statement as given any collection A of open sets, if no finite subcollection of A covers X, then A does not cover X. If we let C as earlier, then collection X minus A such that A belong to A, and applying 1, 2, 3, we see that this statement is in turn equivalent to the following. Given any collection C of closed sets, if every finite intersection of C is non-empty, then the intersection of all the elements of C is non-empty. So this is just the statement of the theorem. Hence the theorem is proved. A special case of this theorem occurs when we have nested sequence, means C1 is subset of C2, C1 contains C2, C2 contains C3, and Cn contains Cn plus 1, and so on. If this is a nested sequence of closed sets in compact space X, if each of the sets Cn is non-empty, then the collection C equal to Cn and belonging to Z plus means set of positive integers automatically has the finite intersection property. Then the intersection Cn and belongs to Z plus is non-empty. Now we will define local compactness. A space X is said to be locally compact at X, where X is the element of capital X, if there is some compact subspace C of X that contains a neighborhood of X. And if X is locally compact at each of the point X at each of its points, then X is said to be locally compact. Because here locally compact is at a point X means X is any arbitrary point of X. If X is compact at each of its points, then it is said to be locally compact. Notice that compact space is automatically locally compact. There are some examples. The real line R is locally compact. The point X lies in some interval, open interval AB, which in turn is contained in the compact subspace closed interval AB. The subspace Q of rational numbers is not locally compact. The space Rn is locally compact. The point X lies in some basis set A1, B1, cross A2, B2, cross dash 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 A n, B n. Cartesian product of this open interval, which in turn lies in the compact space, subspace of Cartesian product of these closed interval. So it means Rn is locally compact. Like R is also locally compact. The space Rw is not locally compact. None of the basis elements are contained in compact subspaces. For if B equal to Cartesian product of these open intervals and these real numbers were contained in a compact subspace, then its closure B bar, which is a Cartesian product of this closed interval and these R's set of real numbers, would be compact, which it is not. Every simply ordered set X having the least upper bound property is locally compact. Given a basis element of X, it is contained in closed interval in X, which is compact. Now we have one theorem. Let X be a space. Then X is locally compact, Hausdorff if and only if there exists a space Y satisfying the following conditions. Number 1, X is a subspace of Y. Number 2, Y minus X consists of a single point. Number 3, Y is compact Hausdorff space. If Y and Y dash are two spaces satisfying this condition, then there is a homomorphism of Y with Y dash that equals the identity map on X. So, first of all, in step 1, we will verify uniqueness. Suppose Y and Y dash be two spaces satisfying these conditions. Let Y and Y dash, if you define a mapping H from Y to Y dash by letting H map be the single point, H map with a single point P of Y minus X to the point Q of Y dash minus X and letting H equal to the identity on X. We show that if U is open in Y, then HU is open in Y dash. Symmetry then implies that H is a homomorphism. Let us first consider the case when U does not contain P. Then HU is equal to U. Since U is open in Y and is contained in X, it is open in X. Because X is open in Y dash, the set U is also open in Y dash as desired. Secondly, suppose that U contains P. This was the case when U does not contain P. If U contains P, since C is equal to Y minus U is closed in Y, it is compact as a subspace of Y. Because C is contained in X, it is compact subspace of X. Then because X is a subspace of Y dash, the space C is also compact subspace of Y dash. Because Y dash is Hausdorff, C is closed in Y dash, so that HU is equal to Y dash minus C is open in Y dash as desired. Now the second step. In the second step, now we suppose X is locally compact Hausdorff and construct the space Y. Let us take some object that is not a point of X denoted by symbol infinity for convenience and adjoin it to X, forming the set Y equal to X union infinity, singleton set of unity. Topologize Y by defining the collection of open sets of Y to consist of 1. All sets U that are open in X. Number 2. All sets of Y minus C where C is compact subspace of X. We need to check that this collection is in fact a topology on Y. The empty set is a set of type 1 and space Y is a set of type 2. Checking that the intersection of two open set is open involves three cases. U1 intersection U2 is of type 1. Y minus C1 intersection Y minus C2 which is equal to Y minus C1 union C2 is of type 2. U1 intersection Y minus C1 and U1 intersection X minus C1 is of type 1 because C1 is closed in X. Similarly, we can check that union of any collection of open set is open because union of U alpha is equal to U, it is of type 1. Union of Y minus C beta is equal to Y minus intersection of C beta. This is equal to Y minus C is of type 2. Union of U alpha, union of Y minus C beta is equal to union of Y minus C minus Y minus C minus U, which is of type 2 since C minus U is closed subspace of C and therefore compact. Now we show that X is a subspace of Y. Given any open set of Y, we show that its intersection with X is open in X. If U is of type 1, then U intersection X is equal to U. If Y minus C is of type 2, then Y minus C intersection X is equal to X minus C. Both of these sets are open in X. Conversely, any set open in X is a set of type 1 and therefore open in Y. This is by definition. Now we will show that Y is compact. To prove that Y is compact, let A be an open covering of Y. The collection A must contains an open set of type 2, say Y minus C, since none of the open sets of type 1 contains the point infinity. If we take all the members of A different from Y minus C and intersect them with X, they form a collection of open sets of X covering C. Because C is compact, finitely many of them cover C. The corresponding finite collection of elements of A will, along with the element Y minus C, cover all of Y. To show that Y is Hausdorff of, let X and Y be 2 points of Y. If both the points X and Y lie in X, these are disjoint sets U and V open in X, containing them respectively. On the other hand, if X belongs to X and Y is equal to infinity, we can choose a compact set C in X containing a neighborhood U of X. Then U and Y minus C are disjoint neighborhood of X and infinity respectively. U is a neighborhood of X, Y minus C is a neighborhood of infinity in Y. Now the third step, we will prove the converse part. Suppose a space Y satisfying condition 1, 2, 3 exists. Then X is Hausdorff because it is a subspace of the Hausdorff space Y. If X belongs to X, we show that X is locally compact at X. Choose disjoint open sets U and V of Y containing X and the single point of Y minus X respectively. Then the set C equal to Y minus V is closed in Y, so it is compact subspace of Y. Since C lies in X, it is also compact as a subspace of X. So it contains the neighborhood u of x. Thank you.